What if they don't follow that? Like if there are bad actors that are throwing out transactions that they know can't succeed, that are going to be inferior in some way, and just clog up the system, that can certainly happen. In fact, dealing with denial of service attacks is a particularly prominent problem for blockchain systems. So we need a way of vote, and we need a way to pick between different blockchains, conflicting extensions of the blockchains, that guards against denial of service. Well, how do you do that? One idea is to make it expensive to spam the network with bad transactions. And we can't make it especially expensive to communicate a suggestion, but we can require that each suggestion comes with some proof of work that the party suggesting the transaction has spent some real resources on it. Okay, how do you make sure that a party invested some effort in it? Well, we know certain problems are difficult to solve, and we can make them arbitrarily difficult to solve, such as finding a nonce that if we add it to the information we would otherwise hash for this block, causes the resulting hash code to have all zeros at the front, say. So if that's your constraint, that others will only consider extensions to the blockchain that keep the new hash code with leading zeros, then because we're using a good hashing function here, we know that there's no easy way to go backwards from a desired hash to the nonce that you want. Instead, you can only do brute force, and you're going to have to try this many different nonces and do that many runs of SHA-256, say. So this is how proof of work works in Bitcoin specifically. All of the hashes that extend the blockchain have to be found by picking a suitable nonce. Finding a nonce that makes it work out is a hard problem that requires real computational resources. And it's easy to scale this difficulty in Bitcoin by just increasing the number of zeros that have to be at the front of the number.